My presentation. So firstly, I will give a brief background about the metal-ion battery, also the hybrid sodium battery, and and then so I will introduce the key material of this hybrid sodium battery. So the how to prepare the solid electrolyte and his stability. Certainly, I will introduce one gel cathode. So by using this cathode, the sodium battery can be cycled for a long time. So this is a very good result. And then I will explain the electrochemical performance by comparing this quasi-solid-state battery with the sodium oxygen battery. So, and at last is the conclusion. Okay, as we know, due to the severe energy limited and the environmental pollution, so many countries are developing the electric vehicles with a high energy density. As we know, at the moment, the commercial lithium battery has been applied into the electric vehicles, but the problem is the low energy density. So therefore, the electric vehicle only run a short distance. So many people hope the battery with a large energy density. So therefore, many researchers are focusing on the developing of the high energy density battery. So for example, at the moment, many researchers are focusing on the all solid state lithium battery, also the lithium sulfur battery and the lithium battery. And from this figure, we can see, so compared with other batteries, the lithium battery has a high energy density. Also, it has a low cost, so it will attract much attention. So, and this figure shows the developing map of the battery program. So many countries hoping for example, in the 2025, they hope the battery has an energy density about 400 watt-hour per kilogram. So for example, in China is named as Made in China 2025. In the case of Japan, is Japan raising target. Also in the case of the American, they hope the battery has the 500 watt-hour per kilogram. So it named the battery 500. So among these batteries, so this sodium metal-ion battery attract much attention. So this table summarizes the different kind of the metal-ion battery. It includes the zinc-ion battery, aluminum-ion battery, magnesium-ion battery, also the sodium, also the lithium battery. But in the case of these three batteries, zinc, aluminum, and magnesium, they are just the primary battery, so they couldn't be charged. In the case of the sodium and the lithium, so they can be they are batteries, they are rechargeable. So although all of the metal-ion battery has a high energy density because the cathode is just from the oxygen or the air, but all of the battery are facing a lot of challenge. For example, in the case of the zinc-ion battery, the hydrogen evolution. In the case of the aluminum-ion battery, the self-discharge. In the case of magnesium-ion battery, the low cooling efficient. Also, sodium battery is because it's an active metal, so it's a problem is safety. Also, in the case of the lithium battery, the cost and the safety is a challenge issue. And this figure summarizes the cost of the batteries. For example, for the cost for the per kilogram hour. So here is the sodium battery. It means the cost for the sodium battery is the smallest, so it's very cheap. Therefore, it attracts much attention. And here I compared the sodium battery and the lithium battery. So as we know, the most important advantage is the in the case of the sodium battery, it's an abundant element. Therefore, the cost is low, so it's much cheaper. Also, this figure shows the comparison of the sodium battery and the lithium battery. So compared with the lithium battery, so sodium battery has a low over potential. It means it has a high energy efficiency. Also, for the formation and the deformation of the sodium superoxide is a main product for the sodium battery. So it's more energy efficiency than the lithium superoxide. So it leads to battery has a good performance. Also, in the case of sodium, it has a high ionic conductivity in electrolyte. Therefore, we focus on the sodium battery, and this slide shows the 4 types of the battery. It includes the aprotic, aqueous, solid-state, and the hybrid. In the case of the aprotic, also it's called the non-aqueous. The problem is discharge product easy to clog the electrode, so it couldn't be cycled for a long time. Also, we can use the electrolyte by using the aqueous electrolyte. But we know if the anode is lithium or sodium, it's very easy to react with aqueous electrolyte. So the problem is the safety. And in the case, also we can use the solid state. Of course, in the case of solid state, we can use the solid electrolyte. Also in between the solid electrolyte and the anode, also the solid electrolyte and the cathode, we use a polymer to modify the interface. In that case, it leads to the battery with a large inner resistance. It leads to the low energy density. Also, the first one is a hybrid. In the case of a hybrid, firstly, I used the solid-state electrolyte. And then, in the anode case, I use the non-aqueous electrolyte. In the case of the cathode, we use the aqueous electrolyte. Therefore, the problem of the aqueous and the non-aqueous can be overcome by using system. Also, we didn't use the polymer electrolyte, so it has a relative high ionic conductivity, and it's lead to the battery with a high energy density. So our research is focusing on this hybrid sodium battery. In order to prepare this sodium battery, the most important thing is we should select the solid-state electrolyte with a high ionic conductivity and has a good stability. So this figure shows the different solid electrolyte with different ionic conductivity. So from this figure, we can see, of course, polymer, the ionic conductivity is low, but in the case of sulfide, it's unstable in the air, also in the moisture. So therefore, the NASICON structure, also the beta aluminum, has a relative high ionic conductivity. But in the case of the beta aluminum, but in the case of high temperature, it's okay. Low temperature, the ionic conductivity is still very low. Therefore, we use the NASICON structure solid electrolyte as the separator for the hybrid sodium battery. It has a high stability, high ionic conductivity, also the wide electrochemical window. But of course, the problem is the interface contact because it's a solid, inorganic solid. Okay, so this is the preparation of this NASICON ceramics. So it was prepared by the two-step sintering, and we can obtain the ceramic with the high ionic conductivity. The specific density is 3.22, corresponding to 98% of the theoretical specific density. So it means it has a low boundary resistance. So this measures the result of the ionic conductivity. So the ionic conductivity at room temperature is about 1.3 multiply 10 to the power of -3 at room temperature. So it's acceptable for using the sodium battery, also the solid-state battery. And here I compared our NASICON structured solid electrolyte with the lithium-based solid-state electrolyte. So this is a lattice. As we know, this has been commercialized by the Ohara company in Japan. So our NASICON structured solid-state electrolyte has a high ionic conductivity than the commercial lattice case. And also we investigated the stability of this NASICON structured solid electrolyte. Because this solid electrolyte should be immersed in the aqueous electrolyte. So we check the stability of this electrolyte in different in the aqueous electrolyte with different pH values. Also, we checked the SEM of the solid electrolyte in the organic electrolyte. Both of these results demonstrate that the battery, the solid-state electrolyte has a good stability. Okay, so here is the comparison of the hybrid sodium battery with the non-aqueous sodium battery. So the cell reaction is different. In the case of the hybrid, so we can use the alkaline or the aqueous electrolyte. Also, we can use the acidic or the aqueous electrolyte. And in the case of the alkaline, so the reaction is sodium reaction with oxygen and water to form the sodium hydrate, and the water is 3.11. Energy density is 2,060 the kilowatt per kilogram. And this is the advantage of this battery: the soluble discharge product and the high practical power and energy density. The most important thing is this battery can be worked in the air. So it's the most developing of this battery. But we know at the moment, most of the, for the lithium air battery or sodium battery, actually they are the lithium oxygen battery and the sodium oxygen battery. It's difficult. These batteries are difficult to work in the air, but in our case, it can be worked in the air. So this is the most important advantage for the hybrid sodium battery. And this is the developing of this battery. So firstly, it was prepared by the Professor Hayashi in Tokyo Institute of Technology. He's my supervisor of the postdoc. Also, this battery was developed by Professor Kim in Korea. They prepared the rechargeable sodium battery based on the seawater. And recently, our group prepared this battery by using ionic liquid electrolyte. Also, we use the liquid anode, and we developed the some new catalyst for reduce the overpotential. Also, recently we use gel as the cathode to assemble the quasi-solid-state sodium battery. And here is the power density of this hybrid sodium battery. So in previous is only 11 microwatt per centimeter. So recently we can prepare this battery about 39. Of course, our target is 100. So we are still working on this new battery system. Although this battery has a lot of advantage, but there's a lot of challenge. As we know, the safety, because it uses the sodium. So also it has a problem of the contact between sodium and the anode electrolyte. Also, we should improve the ionic conductivity of the solid electrolyte. In the case of the cathode side, so as we know, the aqueous electrolyte is easy to evaporate. Also, we need to develop the catalyst with the bifunctional for the OER and ORR, so to reduce the overpotential. So in order to solve this challenge, we already run a lot of work. Firstly, we prepared the MOF-derived nitrogen-doped carbon nanotube as the catalyst for the hybrid sodium battery. So this is the structure of our catalyst. It can be used the OER and ORR bifunctional catalyst. And the result that indicate that our catalyst has a good performance than the platinum carbon and the rhodium oxide. So this is the our work about the catalyst for the hybrid sodium battery. Also, in order to improve the performance of the safety of this battery, we replace the sodium with the a liquid. So by using the BP and DME solution to replace the sodium. In this case, by using this liquid anode, so the interface resistance between NASICON and anode can be reduced. Also, this battery demonstrates the very high energy efficiency, about 95.3%. So the over potential is very small. So it's a very good result. But as we know, in the case of the hybrid sodium battery, so the evaporation of the aqueous electrolyte is a very challenge. So therefore, recently we use the gel cathode to prepare the quasi-solid-state sodium battery. By using this gel, so this battery can be cycled for a long time. So this is the structure of this battery. Here is the gas diffusion layer, and this is a gel cathode. And then NASICON, and here is the metallic sodium. So it can be worked in the real air to for a long time. And firstly, I will introduce how to prepare this gel electrolyte. So this is a reaction, just the interact between the single wall carbon nanotube and the ionic liquid. So after the pi cation and the pi electron interaction, so the single wall carbon nanotube was separated, and then so we can get this gel. It is hydrophobic. Also, it couldn't be faired. Also, this gel has a good stability and a very large electric chemical window. Also, we measured the ionic conductivity. So it's about 1.3 multiplied 10 to the power -3 Siemens per centimeter. So it's very high. And then we used this gel cathode in the quasi-solid-air battery and the solid sodium oxygen battery. So this is electrical chemical performance. So in the case of the sodium-ion battery, the voltage gap is smaller than sodium oxygen battery. So it's very interesting because normally the sodium-ion battery is poorer than sodium oxygen. And also it has a large discharge capacity, and at a different current density is more better in the case of the sodium-ion battery. Most important thing is this battery can be cycled about more than 500 hours. So the cycle performance is better than sodium oxygen battery. And we analyze the discharge capacity, also CV and the EIS result. So in order to analyze the region why this battery, sodium battery, is better than sodium oxygen battery, we use the in situ XRD to analyze the performance of this battery. So this is a discharge at the discharge result at a different state. So from this result, we can see the product of the sodium battery is the sodium hydrate. So in the case of the sodium oxygen battery, so the main product is the sodium dioxide hydration. So this is the main difference for the discharge product. And then I explained the region, the mechanism for this two kind of the battery. Okay, firstly, oxygen obtain the electron, so it can be formed to the oxygen plus -2, and then it will react with the sodium plus to form this sodium dioxide. In the case of the pure oxygen, so because it just has a trace water, so this product uh, combine with water to form the sodium dioxide hydration. But in the case of in the ambient air, as we know, in the real air, it has the humidity is very high. So in this case, the sodium dioxide react with the moisture and then form the sodium hydrate. In the case of the sodium hydrate, it is has a high ionic conductivity. Also, is soluble, so it's just on the safe surface of the electrolyte. Therefore, in this case, the battery has a good performance than the sodium oxygen battery. Okay, now I will give a short summary. So here I introduce the challenge of the hybrid sodium battery, and we already prepared the NASICON with a high ionic conductivity. Also, in order to overcome the challenge, for example, we use liquid anode and we use the modified MOF derived carbon nanotube as a catalyst. Uh, the most important result is we use the gel electrode to improve the cycle performance. It can be worked for long time in the real air, so it's a new result. And then I will thank the financial support and the collaborators. Here is the group member of